Well, looks like we're just about there. Welcome back, everyone. Well, we're on midterm week, so first thing we want to say is congratulations for getting to the halfway mark. We just have to do everything we've done so far all over again and get through the next 8 weeks. With what we've got going on today, we're going to be looking into exponential growth and decay. And this is kind of a callback topic from college algebra, but are in an exciting position where we can look into this content once more and see what's going on from the calculus side of it now. There's a differential equation in the background that we can analyze and work with the solution at the same time to answer these kinds of questions. So a lot of this might be kind of review, kind of a callback concepts, but we're just seeing it through a stronger lens with our abilities with calculus so far. And then what we've got going on for this week is nothing too special. At the end of the week, right around Friday, I'm going to grade quizzes, update your current course grade, bring in the web assigned homework, and wherever your grade standing is around Friday of this week or Saturday, if it takes me longer, that's going to be your midterm grade, just at what your standing was halfway inside or halfway into the course. Well, any questions at the moment? Okay, then the next more interesting thing that happens with midterm week is that we're getting into our second exam week. And this is going to start off the cycle. Once we're done with this week, whatever topic that we have fully completed is going to be the last section that appears on our second exam. Looks like section 3.6 is going to make it, but I don't know about 3.7. We'll need to start it, and it might get finished in the next week. That means it's going to really fall onto the third exam. Also, when we're on this week right here, Tuesday, the 11th, is going to be a pretty normal day for us. But when we come back on Thursday, the 13th, you'll be able to see all the information for the exact coverage on the exam, the review props and such. I'll be publishing them starting on Friday of this weekend after midterm grading. And that means on Thursday, the 13th, even though there's no review date built into the schedule, I'm always happy to start class by taking questions. And if you have a lot of questions, for the sake of reviewing exam 2 content, I'll be happy to address all of them, even if it takes a lot of time. So that will be our second impromptu review day on the 13th. Well, that's the plan so far. Any questions at all, folks, before we get started? Okay, let's dive back in. So now in section 3.6, we're almost done with chapter 3, which is kind of exciting. And this is really our first big application section of the entire course. Chapter 4 is going to have a couple more on optimization with the first derivative. But here's what's going on with this problem right here. Notice that we have a pretty bizarre looking equation. It's an equation for which the unknown of this is the function y itself. On the left, we're taking the derivative with respect to with respect to time t. And on the right, we just have k times the unknown function y. That makes this whole equation a differential equation. It's a differential equation because, well, the equality there implies directly it's an equation. But if there's a derivative inside the equation, now we call it a differential equation. And the unknown is not a number x, it's not a number t, it's the entire function itself. The unknown is the function y equals f of x, which would satisfy this differential equation. And by satisfying it, what I mean is if we differentiate whatever the solution is to that, we should be able to find a constant k multiplied by the original function itself. That's what the solution would be. And kind of a weird expression then. But let's take another look into that differential equation. The way this one was derived was through this information. We're considering a quantity, y of t, or a value, which is going to change with time, fluctuate with time. It could be A population of organisms, maybe cells on a petri dish. It could be a mass, something that's disintegrating due to radioactivity. It could be a population of humans. It could be an amount of money in a bank account. Any of those kind of quantities would satisfy this setting right here. So it's a quantity at time t. And then it says, if y of t is some quantity, that's what we're trying to solve here. Y equals, let me make this a little bit more comparable. Let's call it f of t, since t is the unknown independent variable. It goes on to say, if the rate of change of y. The moment they're talking about the rate of change of y, it's indicating dy dx verbally. If the rate of change of y with respect to t is, that's just a literal equality here, proportional to its size y at t at any time t, then you get this expression here. This is the trickiest thing about the whole expression. Something being proportional to its size means there's some constant k that's multiplying the size of the population y of t. K is going to be that constant, which we'll refer to as either the relative growth rate or the relative decay rate. But the important thing that we said here is that K is a constant. That allows us to recall our differentiation formulas that involve that constant K. If we try to differentiate it on its own alone, it would go to a 0. If we differentiate K times Y, well, K would survive through the constant multiple rule. So that's the information so far. dy dt is the rate of change. Y is a positive quantity. And that now tells us if K is bigger than 0, this whole thing is positive. That would tell us if the derivative is positive, the function itself is growing, so we call it relative growth. If K is negative, however, then this is a negative quantity on the right. We're saying the rate of change of the population size is decreasing if it's negative, and that's why we would call it a relative decay rate, or the law of natural decay. Well, that tells us everything about the equation, but it doesn't tell us how to actually solve this equation. And actually, college algebra, when this is introduced, is pretty weird. College algebra starts by telling you the solution and never telling you the equation underlying everything. That's really weird that you study the solution with never discussing the differential equation, but it makes sense. It's because we're in college algebra. It's an application that's useful already to college algebra. And we don't have the time to talk about derivatives when this topic is introduced. So we completely ignore all of this in a college algebra setting and say the solution to this sentence is this classification of functions. Y of t equals y at 0 times e to the power kt. Solves the differential equation above, dy dx equals ky. So that's the statement of the problem. The problem is here. The solution to the problem is down here. Let's say that just very verbatim right here. This is the solution to dy dt equals ky. Well, an exponential function shows up, and now there's a lot of different moving parts being involved here. We highlighted K as being either the relative growth rate or the relative decay rate. Y of 0 has a different value, or a different way we would indicate it. We would consider y at 0 to be the initial value. Or we could call it the initial condition. Or we might call it the initial size of the population, or the initial amount of mass. But as a context list problem right here, we'll just call it the initial value. And if we have stronger context, we could rename it to initial population size and so on. So these are all the moving parts of the solution to the differential equation. All we need is the initial value, a growth or decay rate, and we fully specified the solution to that up there. An example 1 is meant to just be kind of a fast problem where we go through these moving parts through this definition, theorem 2, identifying key parts. So here's a growth model. I'm calling it population growth because of that 0.0235 being a positive quantity. If there's a negative sign here, this would be a relative to K model. This describes the population size for a country, who knows what country, at time t measured in years. So now we have context, and that means we can answer these two relative questions here. What is the initial population size? And what is the relative growth rate? I'll go first. For relative growth rate, all you're looking, oh, hang on, let me fix something. We're doing growth rate in blue, and this is a really bad time to change that around. Let me try to keep this consistent all the way through the notes. All right, starting over, which portion of the function represents the relative growth rate? That's the part that's conveyed up here, whatever the K value is, but it's the value that's multiplying t per time. So we can just say right away, K equals 0.235. It's a constant, like we were saying up here above, and so we can't put in the variable t, or else it would no longer be a constant at that point. So that's indicating the growth rate of the problem. Next, for the initial population size, we're just looking at this area of the solution to the differential equation. That means the 750 just right there has got to be the initial population size. So we'll write that out as, well, when you're talking about initial population size, you are talking about the initial value, y at 0. It's from this part right here. It's not a bad idea to just say y at 0 equals 750 people, because it's a population of people in the country. So I'm expressing it, the actual part of the solution, K equals that for the growth rate. Another actual part of the function, y at 0 is 750 people, to tie together those two concepts. And now that we wrote that out, y at 0, well, that was just one part of the function, but it's also honest function notation. If you have p of t, or hang on, let me start over on this. I did say y at 0 because I was matching up that, but what would be a better symbol to put there in place of y? Anyone see a better symbol than y for this context? Definitely p, good call on that one. So don't do as I did. I mean, it's not terrible. You're thinking about the initial value if you use y, but you also want to remind yourself of the context. It's a population size. So we should say p at 0, and also if the function's indicated as p of t, that location here wouldn't be y of 0, we would call it p of 0. Okay, that's our fix on there. And now the other thought I was having with this is not just a placeholder for a value, it's also honest function notation. And we could write it out this way. If this is our p of t function, then p of 0 means you take 750 e to the power of the 0.235 times, well, there's the input t right here in the function. That value of 0 says we're passing to t the input of 0 now. But then that means we're just getting 750 e to the power of just 0. When we multiply out the exponent here, e to the power of 0 is 1. And so this just turns into 750 people altogether. So this is really just honest function notation, which is why we write y of 0 here. That's where it goes. And it is the function value itself all in one. Lots of weird things going on with the p of t function, as well as the differential equation. Last thing we'll do, though, is to show, we haven't done this at all, that this is really the solution to the underlying differential equation right up here. So that's going to be really now the new content, the content that they can't talk about in the algebra class, but now we can suddenly bring into view because we can talk about the derivative. Let's show that this function is a solution to the differential equation as our last step on this one, and then we'll move into more routine kind of problems. Any questions or comments at the moment, however, folks? Okay, let's take a look into the solution to this. But first, I want to write down just two things that we're going to often be working with throughout these notes. So they go like this. We use a slightly different format. dy dt equals ky. So this is contextless. Y can be now anything, but that's the underlying differential equation. And this has solution. The solution is going to be y at t. We're kind of letting y be double duty here as the output function, and we're using function notation. So think of that as a f of t, or no different than p of t here, now that we had context. The solution y of t is equal to y at 0, e to the power kt. And let me just redo those bits right there for the color coding. Okay, we'll be working with both of these out all at once. Oftentimes we focus on this because that's where majorly our training is from algebra, but we have to identify when this comes in. So that's going to be a big part of the notes. When is the question about the derivative, not about the actual solution to the differential equation? But with that in mind, let's scroll up to here. For showing dp dt is really kp, we have to take our solution and just differentiate it. So we begin by saying dp dt equals the derivative with respect to t of this entire function right here. So let me write it in as 750 e to the power of 0.235 t. And this is how it starts off. So to show that this really works, really another way to say this is we're just showing that the p of t function provided here, we copy down here, is really the solution, like we just specified down below, to the original equation. Only way to know is to check it, and here's the check. First rule we're going to use, though, is the good old constant multiple rule. 750 as a constant is multiplying, so it is completely unaffected by differentiation. We just go 750 multiplied by ddt, derivative with respect to t, of a base c exponential function, e to the power 0.235 t. And I think this color coding is important, so let me just do a really quick job of bringing it back. And that's step one, just the constant multiple rule. Step two, right over here, where the derivative is indicated by, this time, d by dt instead of the prime symbol. On this next step, it's a chain rule problem. So let's carefully navigate through this one. As a chain rule problem, this one is tricky because it's an exponential function. We talked about these being slightly non-standard in the chain rule process, but you can still identify that this is a function, 0.235t, that's going inside the outer function e to the t. So that makes this derivative that we handle second the inner function. And this one, the base c exponential itself, you could view it as e power t. That's the derivative we handle first, the inner function. The inner is y equals e to the power of t. I'll specify this way, just as a better view of what's going on for the chain rule analysis on this one. So on next step, let's write out 750 stays in position times, for this derivative, we first go e to a power of something, multiply by the derivative of respect to t, whatever that something happened to be. And it was the inner function, 0.235t. That means it copies in this location. Parentheses here are superfluous, so we're going to drop them on the next step. It's just a way to say something plugs into that location. And then it goes over here, where parentheses are a little bit more important, 0.235t. Okay, so last derivative to take is right here. That's what we mean by 2. We're differentiating 0.235t second. It will be our final one to take. As now the output to this is going to be, first copy in 750, e to the power 0.235t. And now finally, derivative of this Well, it's a degree 1 linear function, so we just grab the slope, 0.235t. Excuse me, 0.235. The derivative of this with respect to t makes t fall off, drop as a variable. So this is what it looks like so far. All derivatives done. And now we have to show, did it really solve this? First, let's pause on what we've gotten right here. Any questions about just doing the derivative itself? Okay. Next thing we should do to really check that we've solved that differential equation, let's come back up here and recall what is the format of our function. We need to find, to check that equation is satisfied, the k value itself. But that was 0.235, and here it is. K has emerged in this location. If we take another step to just reorganize all of this, we could say it equals 0.235 multiplying 750 e to the power of 0.235 t. And at this stage, there's lots of stuff on the board, but let's take a look at each one of these components right here. 0.235, that is the k value. So on our next line, we can say that this is equal to k. So that's a direct substitution from here to here using part A. And now this whole thing, actually, let me just write in a quick statement. We found that to be k. And this whole thing, eyeball it really closely, and compare it to the given function p of t, it's exactly that given function. So this is p of t showing up again. We started with the derivative of p, the original function. And when we navigate through the derivative, it's like a train track of equalities, but we landed on, all the way over here, k times p of t. That p of t is written as just simply p over here when it's expressed as a differential equation. And that means our work is done. From the left is dp dt, where we started. And by doing a really careful derivative, observing the chain rule in the middle, we were able to make two substitutions to say, yeah, we did end up on kp. That means our work is done, and we can say this shows dp dt equals kp for the given function p of t. So that's our check. It tells us that the formula down here, if we did the same kind of style derivative, it would become this again. So this check, even though it was more concrete, we didn't verify that, it's exactly how it would go as well. It gives us some intuition on why this really is the solution to that equation above. It's because when you differentiate it, that's the format of your answer every single time for these kinds of functions. Well, with all that information, this is the superstar right here. It's not just about the solution, it's about the equation itself. They're both necessary to fully answer these questions coming up. So we'll take this as a big takeaway and screenshot it into the problems for when it comes up. So we'll take a look into this example 2 right down below next. So here's a pretty decent applied problem. This is a laboratory kind of setting, and this kind of stuff could happen. It's a real life situation. Let me put in just a quick takeaway right here. That's just as a reminder. That's a little too big. There we go. And now we can get started on this problem. So imagine with what's going on right here, that you are the head person in charge of the laboratory, whatever this lab is. Maybe this is something at the INL, who knows? And the information they gave us is a little bit weird. We're told that bacteria culture grows at a constant relative growth rate. Well, they're talking about K, and they're telling us that this model, the equation and solution, is relevant. Through that sentence, gives us some context. But their information that's been provided is a little bit weird. Or maybe not too weird. The bacteria count was 600 initially. You know, when you see that, 600 initially, that's kind of nice because they're indicating was y of 0 or p of 0 if we're thinking of population size. It's just that value. I'll go with p, so population of bacteria was 600 cells initially. The initially there means at time 0, so we threw a 0 into that location. And here's the weird part. It was also 75,000 after 3 hours. Let's highlight that bit right there. Really the fundamental technique we need, even to just get started on this problem, is to take this information. It's another value that's going to allow us to solve for y and say, not solve for y, solve for p rather. P at the 3 hours should go in first equals 75,000 cells. A suspiciously rounded number makes it look like a made-up question, but we've got a number. And by the way, you don't have to worry too much about people hand counting these cells. A different student alerted to me that when this really happens in a laboratory setting, imagine this is your Petri dish, your bacteria are scattered around the contents, and a light is shown, a very bright light is shown from below, and each photon that's blocked is presumably blocked by a cell in that Petri dish, and it leads towards the count at a certain time. So that's how these things are actually counted. It's imperfect, but it gets us a pretty good view of what's going on in reality. And neither is these models perfect. It's just modeling the approximate population size. The model might have been accurate at 3 hours, but give it 3 years, there's no way it's accurate. The Petri dish is going to look really gnarly. In fact, at 24 hours, this whole growth model is probably irrelevant. Works over short time frames with unlimited access to nutrients and resources. But these problems, the model will break down in short order if time goes on too long. But we still want to find the expression for the bacteria. We're just modeling reality the best we can mathematically. So part A is asking us to fill in this information. P of t equals p at 0 times e to the power kt. We already have the p of 0 part, so we can throw 600 in right here. That updates the model to p of t equals 600 e to the power kt. So the last thing we need to solve now is the value of k. The moment we have our k value, we have the expression for the number of bacteria after t hours. Well, let's see what we've done. We've used the initial condition. We know it's a growth rate model, so that implies k is going to be positive, but we've never used this information. So this is where we should start on our next step. So this would be step 1, just write down the model. Step 2, plug in the information that you can find in the problem. Step 3, now we're solving for the value of k using another condition. Let's first just start by rewriting it. P of 3 is 75,000. And that's kind of a tough equation to solve when you just look at it at face value like this. Nothing to work with, you absolutely can't divide by 3. It's locked inside the function p. But we have a function p right over here from step 2. Input 3 inside this function, and we'll have a substitution we can make on the left. So our next idea is we go over here, set t equals to 3, which came from that input. So we would get then 600 e to the power of k times 3 equals 75,000. So that's the substitution. 3 went into t. That means it's k times 3. And our major goal here again, solve for k. Now that's doable. First thing we want to do is clear out the coefficient, take the natural log of both sides, divide by 3. So that's going to be our plan of attack. Any questions at all, folks, getting to this step here? Okay, we're well on our way with this. This might again feel like deja vu from other algebra classes, but it's a good review as well, I'd say. To solve this, take 75,000, divide by 600, and nice round number, 125. Doesn't have to be a nice round number. Sometimes these computations get messy, but if you've got something nice and round, it oftentimes gives us a good feeling we're on the right track. So e to the 3k after division is exactly 125. Now, the next concept, we haven't even gotten into differentiating logarithms just yet. So this is actually a good topic before that, section 3.7, derivatives of logarithmic functions, because here we're basically just reviewing logarithms. If we want to solve this equation for k, we do the inverse function for the e to the x, exponential. The function inverse to e to the x is the natural log of x. So we'll take natural log of e power 3k. Which means on the right-hand side, you're dealing with natural log 125. The reason we called the natural logarithmic function is because when we said they're inverses, this is what it looks like on paper. Whatever the exponential has done, the natural logarithm has perfectly and exactly undone it, returning back just the input to 3k. So 3k now equals natural log 125. Final thing to do is just divide by 3. So k equals natural log 125 thirds. And that's the value that's going to be plugged in here. So step 1 was just to write down the equation for the solution, like this. E to the power of this k value times time t. It's kind of clunky to throw all that in. So the way I'd probably write it in is to go natural log. Actually, let's start with t. I'm going to put that in front. Then k is going to be natural log 125 divide by 3. It's kind of a curious way of writing it in. It's a stylistic choice that I made. But the reason for doing it this way is I don't want a huge stacked fraction as an exponent. So I wrote it kind of linearly with a slash going that way. Just makes it a little bit more compressed, easier to analyze. The other thing I did was I put t in front because when you throw in a natural log function, you definitely have to close that parenthesis. But anything after sometimes is misinterpreted as the input to the natural log. Placing it right here is just going to make it a little bit easier when we go to the calculator and actually compute these values out. And by the way, I don't know if folks can see this on the Zoom side. Here's what my Zoom controls look like so far, and I'm slightly concerned because I don't usually see preparing live stream show up in the middle of a live stream that should have been in action. So let me just ask the class, is Zoom working okay so far on your end, or did anything weird happen?
It looks good.
Okay, thanks for letting me know, Riley. I'm going to hope that the actual live stream is also good, but when I go to publish this video, if you come back to it, let me know if there's been a problem with it. I'll find a way to get that corrected. But we did it, folks, for part A. All we've done was complete the model, finding the missing information. And this is the 4-step process for whenever that occurs. Part B is routine computation. Find the number of cells in 2 hours, round to the nearest cell. All it's asking us to do is to compute the number of the cells of this is a better way to say it. Got to be a better way to say it. Population size at time 2 hours, or number of cells at time 2 hours. It's all that's being asked right here. But that means we just take the 2, the input to the exponential growth function, throw it in there, and we're on our way. So it would equal 600 e to the power of 2 times natural log 125 division by 3. Now, if this was a homework question, say like a quiz problem, I would accept that completely, no problems, no questions asked. It's the right value. It's perfectly exact. There's no harm there. If you're doing it as a problem on WebAssign, though, we do have to calculate the value. We have to be really careful about rounding in the middle as well. So it's going to be a little bit tricky. Oh, sorry for missing a chat. Thanks, Abby. I'm glad to hear it's still working. So when you do this as WebAssign, we do have to put it in a calculator. So I want to be really careful with this step because it turns out section 3.6 is one of those sections where I get lots of questions on WebAssign, but they're mostly questions related to actually computing your final answer, not as many questions of getting to this step. So my major comments on this would be this part right here is full credit on quizzes and exams. The approximation is going to be optional for quizzes and exams, but we should still do it because if we get a value that's larger than 75,000, we know we made a mistake in building the model or a mistake in the calculator. So on an exam setting, if you let this here just like that, I give full credit on that. But we still need to approximate the answer, so that's what the next steps are all about. Now, this depends on the calculator that you're using on the exam. Usually it's going to be a calculator about like this. This one is really painful because you have to do order of operations, working inside out, computing as you go. Another calculator that's really helpful is this one. Let me see if I put a screenshot here. Hang on, here it is, calculators allowed on exams. I like this calculator because you can put everything that we wrote in one line right here and just hit enter. So in a lot of senses, this is the easier calculator to work with. Trouble for me though is I can't emulate that calculator. I don't have any technology for that. I can put it in Desmos though. So let's try a couple things on this one. This is a major spot to practice so that we're not humongously frustrated in WebAssign, and we know how to check our answers even if this was an exam question. But when I type this into Desmos, try to do it as well on your end with your calculator that you intend to bring to the exam. And if you hit any snags, we'll see if there's a difference. And I'll do it a different way again to just show about what it should look like on that calculator. So here's my first attempt at this. Desmos calculator is not exactly how it looks like in yours, but it's close. Go 600 times e to the power 2, and I can't hit times there because it drops me out of the exponent spot. Maybe if I go a parenthesis, 2 times, okay, that works. Then natural log, 125, then hit division. At this point, it would look different in your calculator. Division by 3, close the parenthesis, and my output is exactly 15,000. So we're saying at 2 hours into this experiment, you should be getting 15,000 cells. Okay, well, how did we do, folks? Is this about what everyone's getting so far? Okay, glad to hear that. And maybe just one other look at it. This is kind of tricky for me because this can cause a miscommunication. I want to show how it goes in a TI-83 calculator, not because the TI-83 calculator is allowed on exams, only because it's my best way to emulate what's going on the TI-30X2S. This is a harder calculator to emulate. That's kind of strange. But this calculator, not as hard. So when you see this calculator being pulled up, pretend mentally, we're really just using this one. That's the intention, at least. So if I was to type this out in an actual real calculator, here's what it would look like. Left to right, go 600. On your calculator, your exponential is right here, to the left of the number 4. Let's pull this up again. Well, it's not quite to the left of the number 4. It looks like it's way up here. The ln button is close to the very top. So hit that button. Well, hang on. Hit second, and then that button to call up the exponential function, because the exponential is printed in blue. Here I'll go second, ln button, and you should see e to a power pop up next. That's where we're putting everything in the parentheses we see up here on Desmos. So just go 2 times natural log 102. 125, here's where the first most common mistake occurs. You absolutely have to close that parenthesis, because if you don't, you're saying the natural log of 125 thirds, which is different than the natural log of 125 divided by 3. So go division 3 here, close that parenthesis. This parenthesis is now the last part of the exponent. And now let's see how we'll do. We've gotten 1500, and so that's what the output should look like. So here it is, done on, imagine the TI-30X2S. Hide the rest of the calculator to avoid the miscommunication there. And that's the second view on it. Well, one, that's concept, because not only is this a frustrating problem on WebAssign, getting the number exactly due to rounding, inputting issues in your calculator, this also can be massively frustrating on an exam setting. So here's my last piece of advice, things to watch out for when we do this on exam. Looks like this will be exam 2, probably our last section on there. On exam 2, don't put down just the number. I mean, with a comment in orange to the left, I mentioned you don't even need that number for full credit on an exam. And the purpose for this is, on the exam, I want to test the actual calculus, pulling this together. It should be less about just how well you can type on a calculator without making simple mistakes. We'll leave all that for the homework set. So don't put just this down on your exam. If it's accurate, you get full credit, so that you wouldn't lose any credit. But if the number is off, and I have no idea what you actually put in the calculator, I have lost all basis of partial credit. So that's why you should really put this down on your exam. That's where my partial credit comes from. So last comment to say, if this number is wrong, all basis, or I'll say it that way, all basis for partial credit is gone. That sounds kind of sad, but again, I want to, on an exam setting, focus just on the actual computation by hand, the calculus part. Computation through a calculator like this really is more just about checking your answer or doing the computation aspect in WebAssign, since in WebAssign we do need that number for credit. Any questions at all, folks, with those additional comments or just getting the number? Okay, well, let's take a look into the related follow-up questions on there. That's where the screenshot comes into play. Now, part C is a way different kind of question out of nowhere. Part B asks just for the population size at time 2 hours. But part C is saying, how fast is the population changing? What is its growth rate at 2 hours? And it's because of that word right there. This is a calculus question. So this is essentially the new territory in a certain sense. And there's 2 ways to answer this question. You have the original function up here at the red dot. If you want to know the growth rate, you could do it by differentiating that function, taking whatever the derivative is, and plugging in 2 hours. But that's working way harder than you ever had to, because we already know the derivative. That's where this comes into play. Whatever the function is, there's the function above, the derivative is known to be exactly that. So any question that talks about a growth rate or a decay rate, sure, it's a question about derivatives, but you know the answer because that's the underlying equation. We started with the actual differential equation, and the hard work is to get the function out of that. So here's how we would actually answer this. It's a calculus question, but use the differential equation. I'll use a different color there. I'll paraphrase differential equation to just diff EQ. Differential EQ for equation. And the differential equation would be not exactly this one right here by the red dot, because we know the context tells us y is p. It is dp dt. We're also evaluating the derivative. We're doing the evaluation at 2 hours. So we'll say dp dt, evaluate at time is 2 hours, equals k times, instead of y, we'll put in p. Let's use full function notation on this one since we're doing an evaluation and put in p of t. So here's the k that came from that part of the differential equation above. P of t, well, when we go to plug this all in, should really be at 2. So that's the differential equation with the information 2 plugged in. Sorry for folks working in pen. I should have started with just p blank, not p of t. Put in p of 2 rather than p of t. So that's what's going on with here. And notice it means it just intersects with the information from part B now. We can say that this is equal to, trying again, this is equal to, take whatever k is, here it is, so substitute that in, natural log 125 thirds, multiply against population size at time 2 hours, that's the 1500 cells. And that's all we have to do to answer this question completely. So down here, next on this calculator, I'll go natural log 125 thirds. So that's the growth rate. Multiply it by 1500. And this is how fast the population was growing at time 2 hours. 24,141, we're rounding to 1 decimal place, so 0.6. This has a unit of numerator in Leibniz notation, cells, per the unit for the denominator, t was in hours, so cells per hour. And this rate of cells per hour changes all the time. The bigger the population is, as time gets larger, that grows. Then the population growth is proportional to the population size. And so if we did this at time equals 3 hours, we expect a bigger value here. If we do it at, say, 0.1 hours, we expect a smaller value. This is getting larger and larger all the time. The growth rate is just accelerating constantly by that same value there. Well, that was the calculus side of this one, coming up with that growth rate. Any questions at all, folks, with the conclusion here? Okay, it's a dangerous question in a certain sense that that one word, rate, indicated we were using these formulas here. And it's also dangerous because your training and everything we've done till now says to do this problem, you should differentiate the function and then input 2 inside of it. But because we started with the differential equation, none of that had to been done. We automatically knew the derivative from the very beginning on these notes. Really kind of weird in a certain sense. But aside from that weirdness, actually, let's leave this right here in context, just as a reminder that we needed it. Here's the last part of the question. We know at that population size 2, we're at 15,000 bacteria. At population at 3 hours, it became 75,000. So the question now is, when does it reach 200,000? Probably around 4 hours if I had to guess. But we don't want to guess, we want an exact figure. Well, a figure rounded to 2 decimal places rather. This one's back to just being an algebra question, really. Let's to solve this, grab the model. And here's how that follow-up question is going to go. When it says, when will the population reach 200,000? This question here just implies we're solving an equation. Population size at time t equals 200,000. When it's asking when will this happen, it's telling us we need to solve for t this time, as opposed to part A where we were solving for the actual growth rate k. But solving for t on this one's not so bad. We take the entire answer in part A, drop it in on the left-hand side. So next it's 600 e to the power t times natural log 125 thirds equals 200,000. So I didn't do much on here. I just grabbed the answer from part A and put it on the left-hand side. But now it informs us this is the equation we're going to be solving on this problem. Okay, I think we're done with the model there that we derived. Now to solve this, it's really kind of a redo of part A once again. We're going to divide by 600, take the natural log of both sides to eliminate the exponential, and then divide by natural log 125 thirds. So first things first, take 200,000, divide by 600, and it's kind of an inconvenient number, but let's go with 333.3 bar, or 333 plus a third if you prefer. We get e power t, natural log, 125, oh, let me close the parenthesis and then divide, 125 thirds that way, equals 333.3 bar. Let me make that bar a little bit more apparent. Next step is the natural log of both sides. So natural log e power t times natural log 125, close parenthesis, then divide by 3, is the natural log of that large number. Like we mentioned before, through properties of logarithms, we get an immediate cancellation right there. Now the whole equation is, let me put the growth rate in front, natural log 125 thirds times t is natural log 333.3 bar. Last thing to do then to solve for t is you just multiply by the reciprocal of that fraction you see on the left. So t is now equal to 3 natural log 125 times natural log 333.3 bar. All we now have to do is get the approximation of this out, and we're on our way. So we put that away. We're using this calculator here. So this was 3 divided by natural log 125 multiplied by natural log 333. Now, that's not quite right. I put in 333, but it should have really been the repeating decimal, 0.3333 and so on. And this answer, it's acceptable to me. I would look at your work, I would see the answer you got, and if it's in the right ballpark of my expectations, I'm not too worried about numerical inaccuracies. But WebAssign is, so be mindful of how you approximate on your middle computations. If I rounded this to 333 at any step, I might not get the right answer here. Let's put in just one extra decimal point and see how it changes. Changes right there. It went from a 0.08 to a 0.09, and add some more. Looks like it stabilizes finally right here at 0.09. How's that relevant to us? Well, if they asked us to round at any point, and these digits could be influenced by rounding, and we were rounding in a very severe way, we might miss the whole question despite you displaying perfect knowledge on it. It was just a rounding problem. Again, this is the biggest thing that happens at WebAssign for this topic 3.6, which is frustrating. My advice is never round in the middle. If you do an approximation, carry in loads of digits, like 6 digits in the middle, might be a good idea. And if you're still having trouble, just immediately hit the Ask My Teacher button. I'll look at the answers that you've provided in the system. I'll check with the answer that I expect. If I determine looks like you know this topic and it was just a rounding problem, I'll tell you the answer WebAssign expects, because these issues in the middle shouldn't be too painful. So again, if any trouble comes up, don't hesitate to reach out about it. This one's rounded to 2 decimal places, so we'll just say 3.61. hours. And that does the job for us, folks. At population at 3 hours, it was 75,000 exactly. And it reaches 200,000 even before the 4-hour mark. But we shouldn't be too surprised with that exponential there. This is literally just an exponential growth model. It grows rapidly. Its growth rate is proportional, K, constant proportionality, to its population size at any time. So the bigger it gets, the larger the growth rate gets all at once. Well, this is our big problem for exponential growth. Next thing we want to take a look into is exponential decay. I have a couple problems for that one to take a look into. But any last questions or comments, folks, on any of the elements here? Okay, well, here's the next exciting world with exponential decay. Only change is K is negative. Except that, oftentimes with exponential decay, we're interested in something considered to be the half-life in the problem. There's no half-life in our prior problem. There's a doubling time, but we weren't as interested in that one for this concept. But one thing that's kind of interesting about the exponential decay problem is that the half-life is an absolutely fundamental part of it. So much so to the degree of which we have the symbol lambda to indicate the half-life in this context. So this is the Greek letter lambda. The way to draw it is imagine you're doing a variable x like this. You start with 1 slash, but then for the rest, you just go down like that. And now you've got a lambda. It takes a lot of practice to make it look as nice as that. But any approximation of this is going to look like a lambda to me, so don't worry too much about the penmanship. And notice what lambda is tied in with. It's tied in with the decay rate, K. So if you are given the half-life in a problem, then you can use this whole equation to solve for K. This is what it would look like as just a different equation. Solving for K would give us K equals negative natural log 2 divided by lambda. So that's a half-life problem. And honestly, it looks like it's a weirdly specified. It's talking about half-life, but we have natural log 2 in the problem. You would almost expect, if it says half-life, that should be a natural log of 1/2. In fact, it really is. Because of that negative sign here. Again, this section that we're in, we're taking it as an extra opportunity to practice some properties of logarithms themselves. And here's one major property. The natural log, or the log to any base b, of a for any expression to a power p, is the same as p log base b of a. So in other words, the exponent here can move in front as a coefficient through properties of logarithms. And that means when we're looking at this right here, negative natural log 2 over k, that negative sign is an exponent. It's playing the role of p, and p as a negative 1 can go right there now as an exponent. This would turn into natural log 2 power negative 1 divided by k. But then properties of exponents themselves would say that that's the natural log of 1 over 2 divided by k. And honestly, this is the formula that makes way more sense to me because you can just directly write in natural log 1/2 to compare with half-life divided by k. But people made a decision somewhere down the line that 1/2 is not as simplified as introducing the negative constant. And so they went backwards. They wrote the 1/2 as 2 power negative 1. They took the negative and put it in front. And now we're kind of stuck with this formula. Not that we can't change it and use this, but this is now so standard, we may as well be familiar with it because that's how you usually read the information. So after that discussion, this problem is not too bad to get into. I don't know if we're going to solve the entire thing. Let's launch into it a little bit and find a natural stopping point before we call it a day. Well, we're looking into plutonium-239. This one is the not good stuff. This is the one where foreign affairs gets involved and tries to restrict countries refining this. And its half-life is enormous, 24,000 years. We're told a shipment of 1,000 grams of plutonium arrives at a secure location, really secure location just to indicate how dangerous this particular isotope really is, where it's to be stored indefinitely. Maybe this is a signifying that we're doing nuclear non-proliferation type treaties. We're just storing this away now. But in a certain sense, as far as it is concerning with us, that 1,000 grams of plutonium is essentially around forever. Not exactly, the half-life is 24,000 years, but we're all dust by the time it's 500 grams. This is something that, from our point of view, seems like it's around not exactly forever, but it feels like it. Making it a pretty interesting question. So it says here, find an expression for the amount of mass that remains at time t. To guide us on that, let's grab this once again. Just tuck it away down below here. They're not asking us to write down the differential equation. They're asking us to write down the solution, y of t. But we have context. We're talking about a certain amount of mass of plutonium-239. So we'll indicate it this way. M, for mass at time t, is going to be m at 0, the initial mass, times e to the power kt. So that's going to be the decay rate. K is a negative quantity. That's the initial mass. And they did tell us, well, 1,000 grams of plutonium just arrived somewhere. We're not going to say where, secure location. That would be the time at 0. They get the product, they find out how much mass there is, and if it weighs exactly 1,000, no further investigation occurs. That's just going to be our initial mass, and the clock starts. This is time 0 now. So that information right here is just a roundabout way to say m at 0 is 1,000 grams. I'll just use G for grams. That means coming back over here, we can update the model and say mass at time t equals 1,000 grams multiplied by e to the power kt. And I think we're done with that just for the moment. Our next goal is to come up with k itself. It's not 24,110 years, excuse me, but that's the right place to look. Because what they gave us is the half-life. If we have a half-life, we can go to this equation right here, the second one provided, and this directly just solves k in one go. So k equals negative natural log 2 divide by whatever the half-life was given. So it's going to be the time, 24,110. And finally, we got it, folks. That's our figure. So there's a couple ways to go at this point. You could approximate it, but for part A, we want the exact expression. So let's write out for our conclusion. Therefore, mass at time t equals the initial mass that arrived, 1,000 grams, we hope, e to the power of the variable t multiplying this. I don't want to put in t like that because it's algebraically not going to be correct. It's going to be t times. I don't want to include extra parentheses because now it's too abstract to look at. So one clean way to write this all in is to go insert t here. So it's going to be negative t. So t went into this location, and then just write out the rest of the information. T times natural log 2 divide by 24,110. Comma just for us so we can read it with precision, but don't forget in the calculator, you have to drop that comma there. And that means we did it, folks. We have the exact expression. We can now work with it in part B and the follow-up part, part C. Kind of a nice problem in the way. It's kind of nice that relative or decay rate problems often give a half-life. And this is how we'll do those kind of problems when they come up. It means this whole process on the right was really rapid. And to solve this last question, all we need to do is write m at 100,000 years and input the 100,000 years right there for t. Another interesting thing about this problem is you can do a check in the middle on this one. We don't often have an opportunity to do that for part B, but let's do that. Let's see how close in the neighborhood of the right answer we get just by a back of the envelope type of a computation. We had 1,000 grams. We're going to multiply this by something. We know that the half-life is 24,000 years, but let's fudge that a little. Let's suppose it's 25,000 years exactly. That means down here, 4 half-lives have occurred, times 1 half-life is 1 half-life occurring. About 25,000 years has gone by. Increase that to power 2, that's 2 half-lives. Now 50,000 years has occurred. Power 3 is 75,000 years going by. And power 4, this represents 100,000 years going by. So in 100,000 years, that's longer than human record history by a lot. But we're expecting that 1,000 grams of plutonium is this figure here, 62.5 grams, still a dangerous amount. That's not the right figure, but when we go to calculate it down here, we now have a set of expectations. So now doing it exactly, put in 1,000 e to the power of negative. The t value, 100,000, goes in the position of t right here. So negative 100,000 times natural log 2 divided by 24,110, the actual half-life. It's kind of annoying to write in, but that's full credit right there on a quiz or exam. Next step is tricky. Here we're going to try to actually get this figure in by just dumping it into a calculator. First, I'll try Desmos, and then we'll see how we feel about that and see if we need to do it a different way. So in Desmos, go 100,000 e to power. I want a parenthesis for the whole exponent, much like in the calculator. Negative 100,000. So let me double check. That looks about right with the number of zeros. Times natural log 2. That's a little concerning with the value of 0, but let's keep on going. Divide by 24,110. That looks about right. Let me close a parenthesis in a better way. When I put in the right value here, Desmos didn't round it down to just 0. We're getting 56.4, rounded to the nearest 10. And notice that's in line with our back of the envelope computation, where we rounded the half-life to 25,000 years. It really wasn't that long, so we should expect less. The half-lives came just a little bit quicker. So 56.4 grams. Well, that's the entire conclusion of part B. It was just a function evaluation. Part C is going to be a calculus question. And the idea here is if 200,000 years goes by, this just gets smaller and smaller. But the rate at which it's decreasing is also dropping. It starts to stabilize and not change too much at each new 100,000 years we go by. And so the question we're asking now is, after 100,000 years, at what rate does the sample decay? When it says at what rate, we're talking about the derivative dy dt equals ky, or dm dt equals km with the context written in. And when it says decaying, this is an indication to us our answer had better be negative, because a positive derivative here would mean it's a growth rate, not a decay rate. So here's how we answer this question resolutely, exactly, leaving no room for error. We ignore calculus where we differentiate the equation. We use this, the original differential equation, and just say the rate of change of mass with respect to time t, evaluated when t equals 100,000 years, is equal to the decay rate K times mass at 100,000 years. At this point, we're done with that screenshot down below here. We just need to compute all of this, which means we need to put in these values, plug them in. K was this figure, negative natural log 2. Divide by 24,110. At mass at 100,000, let's see, we're rounding to 4 decimal places. But you know, for a question like this, if it's a real WebAssign question, and I told you to round to 1 decimal place here, the system expects you to use the prior answer. And they also check with a fully more accurate answer at the same time. So I said Desmos, WebAssign is actually looking at the order they ask you the questions, considering the values you're being given. So it would be appropriate on this problem to put in 56.4. It would also be appropriate to use this figure here as well. If you went that route, WebAssign knows that that's the more accurate figure. It also checks for that answer. It's kind of nice in a way. Last thing we do is just compute this out. So negative natural log 2 division by the half-life, 24,110, multiplies by 56.4. And that's our decay rate right there. To 4 decimal places, I've got 0.0016 negative. So let's write that in. Equals negative 0.0016. And the units for this will be the grams for the mass per years per time. So, and when we're 100,000 years into this plutonium being tucked away in that secure location, this is how much the mass is dropping by not very much. Let's see, tens, hundreds, thousands, 16 10,000ths of 1 gram. And the value right here gets larger, still always negative, but not as large negative as more and more time goes on. So if this was at 200,000 years, probably 0.00016, something in about that ballpark would be the decay rate then, essentially barely budging at that point. Well, we can't finish the rest of the question down here in the follow-up example, so we'll have to wait for next time before we finish off these notes. But any last questions at all, folks, with our conclusions here? Okay, we'll come back next time, finish off these notes, and then Wednesday we'll also start up our section on dealing with logarithmic differentiation. But have a great afternoon, folks. I'll talk to you all later on Wednesday or Thursday's class. Sorry, we'll get that down one week or another. We're almost midterms, and I think my problem is this class is ran as Monday and Wednesday quite a while, so it's still stuck in my brain. But have a great afternoon, folks. I'll talk to you all on Thursday's class. Yeah, absolutely. I don't think we're going to be able to finish 3.7 on our next class meeting.